Okay.
It really depends which way your house is.
Homeworks?
I don't see them.
Is yours up here, Sarah? Right here?
Yeah.
I should actually let you hold this so that we can. There's been a request to.
Oh, that was the first one.
Okay, so there was a request to go over which problem? Forgot.
211, number 3.
Yeah. Okay. So show that Pn cross Pm box Pn is Hamiltonian if and only if M or N is even, or both. Or both. So in other words, it's not Hamiltonian when M and N are both odd. Okay, so give me an idea of what.
Assume they're both odd.
Okay, assume M and N are both odd. I'm going to draw a picture. Okay, but now what? So what approaches did you look at? Did you try with this problem?
Right.
What?
Like,
Ben?
I did go through by contradiction on one of them saying, let's say that they are both odd, and then finding where they could not both be odd and still be Hamiltonian.
Okay.
What I did was I numbered all the vertices, 1, 2, however many, and then I said when you move along in the graph, you have to go even, odd, even, odd, even, odd, even. But if this is going to start and end on the same vertex, then ultimately you're going to have to do an odd vertex to an odd vertex, which is a contradiction.
Okay, so that's let's tell me more. Tell us more.
Yes.
So you want to label the vertices? Do you want to label them with ordered pairs or
Just 1, 2, m times n.
in any way?
Just sure, yeah.
Like this? Let's see. So this would be 2m. This would be 2m minus 1. Down to this would be what? m n minus. Let's see. m times n minus 1 plus 1, and this would be mn.
Yeah.
Okay. Okay, so this is so I have mn vertices, and if they're both odd, then what can you tell me about m times n?
They're both odd, and m times n will be an odd number.
So are both odd. So
You said odd times odd?
Yeah.
odd times odd is
8.
odd times odd.
Not negative times negative.
Not negative. Let's just make sure. So odd would be 2m plus 1. Let's make sure we understand this. 2n plus 1. Right? That would be an odd times an odd. So we'd have 4mn plus 2m plus 2n plus 1. I think that's the
Odd.
product.
yes.
And that is definitely odd. Okay, so if I have an odd number of points, now what?
If you have an odd number of points, then, like I said, ultimately, if you're gonna close this and thus be in a Hamiltonian, you're gonna have to eventually go from an odd vertex to a
Very
even
good.
vertex.
Okay, so it doesn't matter where we start. Let's imagine that we start at some point that's even. That doesn't really matter. But, because eventually I'm going to get back to that. Okay, so if I, since m, let's see, so do you want to label this in a different way? You probably want to. So this is both are odd. Sorry, that's not right. That's not right. This is 2m plus 1. This is 2m plus 2. That's better. 2m plus 3. Down to 4m plus 2. And so, right? So down here I would have, this would be 2m, 4mn plus 2m plus 2n plus 1. Okay, one more time. I'm taking both m and n are odd, so I'm abusing the notation. We can say m and n are odd, and then I understand I'm misusing m and n. But let's say that the odd number is 2m plus 1, and the other odd number is 2n plus 1. And then I'm just gonna go down, so 1, 2, 3, and so forth down, and keep going. And what's important is that an odd vertex is always adjacent to an even vertex. So note, an odd labeled vertex is always adjacent to an even labeled vertex. Is that clear? Notice, so all its adjacencies. So 1 is adjacent to 2 and 2m plus 2. 2m plus 3 is adjacent to 2, 2m plus 2, and 2m plus 4, and down here would be 3m plus. Let's see. This would be. We'd have to come back down here. What would this number be? Let's see. So I go down to 4m plus 2, and then I come. So I needed a better way to label this. So 2m plus 2. So this would be. I'm going to add m plus 1 to this. So this is 3m plus 3, and this is 3m plus 4. Is that right? Okay. No, that's not right either. 4m plus 3 and 4m plus 4. The next row would be 6m plus 4, and this one would be 6m plus 5. And the most important thing is that every vertex that's labeled with an even label is adjacent to only vertices with odd label. Okay? With me? Is that clear? Is it clear how I'm labeling this? Okay, so now forget the labels, and now let's just look at the Hamiltonian cycle. Hamiltonian cycle. So even, odd, even, odd, even, odd, and so forth, all the way down to this would have to be an odd. But what can you tell me about even times even? Sorry, odd times odd is an odd. So there's an odd number of vertices here. This is odd times odd is an odd number of vertices. So if this was Hamiltonian, I would be going. Wait a second. I would pair these off in pairs, and I would actually pair them off. It would be an even number. Okay, so this would be a contradiction. Does everybody understand the contradiction? Okay, it went very fast. That's a very clever way to do this.
So you're saying it's a contradiction because you don't have an even number of pairs?
Okay, so what I'm saying is that, so they come in pairs,
Uh-huh.
right? Pair, 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 right? This is the last pair. Oh, so that's, this is 2, 4, 6, 8, 10, 12, 14, 2K, an even number. And if that's the end, well, then, this cycle would have 2K vertices in it. Oh, but how many vertices, odd times odd, how many vertices are here? An odd number, one more time. Now, an even number, if it went even to odd and odd to even, then we would have an even number of vertices,
Okay.
necessarily. Okay, so that's pretty clever. Anybody have a different proof? Anybody prove it by induction? Tried. Any other approaches?
So I have a label with two numbers, corresponding.
Okay, wait. So you want to label these? Let me draw it up here again.
Well, I would say, kind of easy you did. It's pretty similar.
So you had ordered pairs.
Yeah,
So this is the first row, first column.
yeah,
First row, second column.
yeah.
First row, third column. And this is the second row, first column, and so forth. And this is the mth row, second column. Nth row, first column. Okay, and finally, this would be the nth row, first column, and this would be the nth row, columns first. So this is the nth. Let's try this right. So first row,
So your
second row, this is wrong. Okay, so this would be the nth row, first column, nth row, nth column. Okay? And essentially the same order.
Well, kind of. It was the, if you eliminate all of the vertices where the parity of the two are not the same,
Uh-huh.
then you're left with a disconnect, an empty graph with more components than the number of vertices.
Oh, okay. So say that again. Okay, so you remove certain vertices
Yeah,
so that you had more components left than
vertices.
the vertices to connect. Okay, we already saw that with on several examples, where if I have several components and I have fewer vertices than there are components, then there's no way to, wrong way. There's no way to connect these if I have more vertices left after we have these components. There's no edges here. There's no edges here. Okay. Okay. Any other proofs? Anybody do it by induction?
The other way by induction.
The other way by, the
Yeah.
wrong way by induction? What? Okay,
No, I
so
mean so.
another
so-
way, a different way by.
No, I mean, we're doing M and M odd imply it's Hamiltonian.
Uh-huh.
The reverse of that statement. I did that one by induction. So
You
if
did that by
if one of
induction.
them's even, then it is Hamiltonian.
Okay, so if it is even, okay, so yeah, this is only the odd times odd, right? The Cartesian product of an odd is not Hamiltonian. Now you have to show that if one or both are even, then it is Hamiltonian. And you did that by induction. Okay? Anybody do it a different way? Does everybody understand there's two parts to this, right? If and only if. You got to show that. Can't happen for odd and odd, but it does happen when at least one is even. Okay? Other questions? other problems with these? Did you, I hope you played around a lot with graphs. That was the idea of the homework. And make sure that I filled up lots of hours during your spring break. Okay. So I have all the homeworks? Okay. Okay, so we talked a little bit about Hamiltonian graphs. I gave you Dirac's result on if you have a high enough minimum degree. If you have a high enough minimum degree, then the graph is Hamiltonian. Of course, that doesn't apply here, which is kind of interesting. This is not Hamiltonian. So P6, I'll make one even. P6, Pn, we know is Hamiltonian. We know that's Hamiltonian because 6 is pretty even. Okay, so this is Hamiltonian. It's got a pretty low maximum degree. The Dirac result requires that the minimum degree, the Dirac result is if the minimum degree of G is greater than or equal to n over 2 in a graph of order n, then the graph is Hamiltonian. That's pretty large. That's pretty large. This is a pretty sparse graph. This is a pretty sparse graph versus this graph, which has a lot of edges. It is optimal. It is optimal. I don't know if we mentioned this, but if you take k n over 2, k n over 2. Okay, so I'm going to take two complete graphs. Then the minimum degree is a vertex here. Minimum degree is going to be n over 2 minus 1. And this is as far from being Hamiltonian as you're stuck. You can't get out of this component. So you can have pretty high degree and not be Hamiltonian. And we've talked about even higher degree. Right? So here's a graph that's also not Hamiltonian. Okay, and this has degree n minus 1 over 2. Okay, so let's make sure this is this is n over 2. This is n minus 1 over 2. This is n minus 1 over 2. And this is 1. Okay, so there are n vertices there. And you can be on one side of the one balloon. You can be on one side over here. You can get all these points up. As soon as you go through this vertex here, you're stuck. You're stuck. The only way to get back here is through that. Okay, so this is not Hamiltonian. It is traceable. It is traceable. What's traceable?
Eulerian path.
Not an Eulerian path.
Hamiltonian.
Right. Okay, so it is traceable. So the optimal example for traceable is where they're disconnected. That's the other part of Dirac's result. Okay, so this idea of Hamiltonicity is difficult, and he gives you the application of the traveling salesman problem. And if you've done any work in computer science, this is the problem. So you're a traveling salesman and you want to visit many different cities, and you want to do it as efficiently as possible without returning to any of the previous cities. Okay, so you'd like to visit each of the cities exactly once, and of course then get back home. So in general, this is what's called an NP-complete problem. So this is out of the scope of what we're going to talk about, but NP-complete means that it's non-polynomial to actually determine whether a graph has a Hamiltonian cycle or not. Okay, so even if I turn a computer on and I'm just The only way to do this is essentially to look at all possible sides. Okay, and that becomes exponential. So there's no polynomial, NP, non-polynomial, possible way to actually determine whether a given graph is Hamiltonian. Now, this idea of applications is where I want to talk about starting right now. So you might think of these graphs. Let's put up an interesting graph. So here's a graph. Okay, so here's a graph. I just put some emphasis in. And what I'd like to know is, for this sort of problem is, can I traverse each of the vertices and get back to the start? So that's the problem we've been looking at here. Well, one of the other things that graph theorists and applied graph theorists in particular look at is the vulnerability of a particular network. So the book doesn't use this term, but so you want a transportation network or a communication network, and think of, when I say the word network, think of a graph. You want there to be some security in being able to remain connected. Okay, think of it as a transportation network. Think of it as a communication network. Okay, and if one of the nodes go down, so imagine one of the cell towers. I guess there's a lot of cell towers, but let's imagine 100 cell towers go down. Then I might not be able to make a call to Dalton. Okay, because the cell towers that I would be using are all down. There's no way to connect to Dalton. So we can think of a graph as an applied drawing of some process. So transportation is another one. Communication. There are lots of different applications of these sorts of networks. Now put yourself as the enemy. Now what you want to do as the enemy is you want to mess up our communication. You don't want us to be able to communicate with one another. You don't want us to be able to get messages out. If we think of this as a strategic network. So what I would like to do as the enemy is I would like to take out, whatever take out means, I would like to take out some of your vertices. Maybe I would blow them up. For example, those 3 vertices. And now you can't get a message from any of these nodes to any of these nodes. I believe that's right. Okay. So what we're gonna be looking at is imagining that these are cell towers or communication centers. How many vertices? Let's talk graphs now. So given a graph G, how many vertices must be removed to disconnect the graph? In other words, I'm going to remove vertices. The graph that's left is disconnected. So, I mean, before we give a definition, let's think about, what if I have just a path? I mean, if I look at a path as my communication network, then certainly everybody, all my vertices can communicate with one another. It's a connected communication network. But it's not too secure, because if one node goes down, if one vertex goes down, then in fact the graph is disconnected. So we're going to define, and I think we started this before break. So I'm going to define the connectivity of K, the connectivity of G. So let G be a graph. The connectivity, and he does use kappa, right? He uses kappa, and then he's going to use kappa prime. Okay, good. So the connectivity, kappa of G, is the order of the smallest subset of V of G, whose removal disconnects the graph. So again, just like with Hamiltonicity, we might think if a graph has a lot of edges, then its connectivity should be pretty high. I should have to remove a lot of vertices before I disconnect the graph. And I say it that way to sort of lead you down a bad path, because this graph has a lot of edges. This graph has a lot of edges, right? This is complete over here, and this is complete over here. That's a lot of edges in itself, and this vertex is adjacent to everybody. But if I remove that vertex, then the graph is disconnected. Okay, so edges isn't necessarily, just like with Hamiltonicity. Edges aren't the sole parameter that's going to help us decide whether a graph is how connected a graph is. Okay, so again, I've got this parameter to give us an idea of how connected a graph is. So let's start with some easy ones, and actually he gives you some in the book, but let's go through some basic ones. So what is a PN? What's the connectivity? What's the smallest number of points that I have to remove from PN so that the graph is disconnected? 1. Hopefully in the middle somewhere, if there is a middle. If it's just P2, then that's right, K2, and that's different. Okay, so PN, the connectivity, the smallest number of vertices that I have to remove to disconnect that is 1. What about CN? 2. Okay. By the way, we haven't put this up in a while. What about the Peterson graph? 1? Did someone say 1? You didn't let me draw the whole thing. Is it 2? What? Can you give me 2? Do you want me to label them? Maybe I'll label them. Let's see. This is 1, 2, 3, 4, 5. A, B, C, D, E. Now this doesn't have many edges. This is a fairly sparse graph. Fairly, whatever I mean by fairly. That's an E there. Right? How many vertices do I have to remove to disconnect that graph? 3. So which, can you give me 3 that you want to disconnect, that you want to remove?
A, 5, and 2.
A, 5, and 2. Disconnects the graph. Disconnects 1 from 3, 4, C, D, B. Okay, so even though this has pretty low degree compared to 10 vertices could have a degree 9 vertex, it's got a fairly small connectivity. Okay, so one more time. Cap of G is the order of the smallest set of vertices whose removal disconnects the graph, and we call this the connectivity of G. So this is defined to be the connectivity of G. So let me, to sort of motivate what I'm going to say next, maybe I should call that the vertex connectivity, because I'm removing vertices. What if now let's look at this network as a transportation network. And now I want to blow up some of your roads. So what's the fewest number of roads that you have to remove so that this graph is disconnected? What about PN? 1, right, if you remove this edge right here. What about CN? 2. Oh, wait a second. The vertex connectivity for PN was 1. The vertex connectivity of CN is 2. By the way, 2, right? You can remove that edge and that edge. What about, and what about the edge, how many edges do I have to remove to disconnect the Peterson graph?
3.
You think 3? Can you find 3 that you remove? 1, 5, 1A, 1, 2. So here's 3 points. Here's 3 points that disconnect the graph. So immediately, this leads me to think that there is a theorem here. By the way, the edge connectivity, let's put this definition up. The edge connectivity is the smallest number of edges whose removal, and this is a little bit different, whose removal increases the number of components. So in particular, we can define the edge connectivity for a disconnected graph. So for example, let's look at that graph. Let me ask this. How many vertices do you have to remove to disconnect that graph?
2.
0.
Yeah, this is a problem. How many vertices do you have to remove to disconnect this graph?
It already is.
It's a loaded question.
It already is.
It's a trick question. So how many do you have to remove?
0.
0. Okay, so if we look at the vertex connectivity as the fewest number that disconnects the graph, this would be 0. Edge connectivity, we play a slightly different game, and we look for the smallest number that increases the number of components. So, for example, for triangles, 2 triangles, how many edges do I have to remove to increase the number of components? So edges. Did I not say edges?
2.
2 edges. So if I remove 2 edges, okay, by the way, can I remove vertices? Okay, one more time. When I remove these two edges, the number of components goes up. Let me put those edges back in and ask, can you remove vertices so that the number of components goes up?
Not in this case.
One more time. Can we remove vertices? So maybe I just gave the wrong definition for vertex connectivity. Can you remove vertices? There's just 6 vertices up there. Can you remove some vertices so that the number of components goes up? No. I mean, in fact, if you remove 3 vertices, the right 3 vertices, the number of components goes down, which is kind of contrary to how we would think. Okay, so for vertex connectivity, we want to assume that the graph is connected. For edge connectivity, we don't need to have connected, we just want the number of components to go up. Okay. Okay, so we have these 2 parameters. So at your tables now, so here are some problems to look on. So this is all from this is from section 6.2, just 6.2. So again, we've got a minimum vertex cut and a minimum edge cut. Okay, so what I'd like you to do is look at, there's some interesting graphs here. So figure 6.2.1. Well, these are small graphs. There's just six vertices here. Let me repeat. What you're trying to do is you're trying to find, in general, the smallest number of vertices so that the number of components goes up. So that isn't what is asked. Can you find a cut? Notice I, and I is asking you specific questions. I want to ask first, what is the vertex connectivity of 6.2.1? So at your tables, talking out, it's only got 6 vertices. I assure you it's less than 6.
Two 38. 6.2.1.
6.2.1.
Used this graph before, I don't remember what problem. I remember drawing it. What did he say?
I can do it with 3 vertices.
The vertex. Vertex.
It's familiar.
I know we were just like, oh yeah.
Oh, and
Oh yeah,
we're
because I'm
doing
gonna have the answers right there.
Sorry.
That must have been like the last
To have written that already. Because the
Vertex,
next thing is going to be
vertex
disaster.
connectivity.
That page.
I can definitely do it with 4.
Do you like C and G here?
Okay, C, D, and U. And then
So you, but because of just like all the way around, it has to be more than one. It doesn't isolate one. So if we take out all.
Because then the only thing that A and E are connected to is each other.
yeah, yep. Cool. You're good at this. Yeah, okay, so that's cool because you can see that everything in here is connected to. Pull up the description. Exactly right. I'm trying to say why. Oh, okay, yeah. So then here are disconnected sets. So if you can find 2 sets of vertices that are not connected to each other, then remove everything else. No, that doesn't sound very helpful.
I mean,
By the way, as you're thinking about this, I mean, this is a pretty simple idea, but strategically, if we're actually looking at applied graph theory, this is a pretty important concept, both of these concepts. And the fact that it's hard, at least what seems to be hard to figure out, makes the problem that much more interesting. You all done with 6.2.1?
Not C. I'm trying,
I think it must be more than 2. I tried everything.
Oh, I thought you were reading.
What you're saying is that the minimum degree has to be greater than vertex.
Yeah, an upper bound.
Uh-huh.
Yeah, because you could just find the one with the minimum degree.
No, 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 if you remove,
Right.
okay. So here's an observation. Here's a theorem. Here's a theorem.
Sounds good.
I'm putting quotes around theorem. Maybe you want it to be theorem. The edge connectivity, kappa prime. Did I tell you that that's kappa prime?
No. Kappa
prime of G is less than or equal to the min degree of G. Why is that?
You could look for a vertex minimum degree and then just remove all the vertices. So it's
All the, so this is the edge connectivity.
oh, I'm sorry. I was thinking vertex.
Just change the word vertex to edge.
I mean, I guess just take all the adjacencies, take the minimum degree and just remove all the edges coming out.
Ah, there we go. Okay, so we find a vertex of smallest degree, which is actually, that's not a hard problem. And I want you to be thinking about what problems are hard and what problems aren't hard. Determining the connectivity in general might be difficult. But I can go around my network, I know how many edges there are at each vertex, so I know every degree. I find the smallest one. I'm pretty good at finding the smallest number out of some number of numbers, usually even 1,000,000. I could find the smallest number. I find that smallest number, and I remove exactly that number of edges from that point, and the graph is disconnected. So here's a theorem. The edge connectivity is less than or equal to the minimum degree. Do we have the same result for connectivity? I find the smallest degree and I remove all the vertices adjacent to that vertex. That vertex is going to be isolated. It may be the only vertex left, but it is going to be isolated. So this works for both the edge connectivity and the vertex connectivity. Okay? All right, so now back to 6.2.1. So, vertex connectivity, let's just quickly look at the degrees of these vertices. Starting at A has degree 3, B has degree 4, C has degree 3, U has degree 4, V has degree 3, W has degree 5. So what can you tell me? Can you give me a bound on the let's start with the edge connectivity. 3. So I look at, pick any one of the vertices, I look at vertex A, and I'm going to remove AW, AU, and AB, those edges. And that disconnects A from BC, V, U, W. So it's at most 3. Are there 2 edges that disconnect the graph? Right, we only have a bound. We only know that the edge connectivity, so for 6.2.1, is it 1?
6.2.1.
no A or something, it's 0.2.1. We just know at this point that the edge connectivity is less than or equal to 3. What about the vertex connectivity?
Same.
Same thing. Remove those same vertices. So, by the way, this is a kappa. Doesn't look like kappa sometimes. Can you disconnect the graph by removing 2 vertices? Should we just take your word for it, V? Yeah, this is hard. This is hard. It's only got, this graph only has 6 vertices on it.
Where these are less than.
All I have to do is look at 6, choose 2, 15 pairs of vertices and remove them, and see if it always leaves a connected graph. I'm being facetious. 15. You don't want to really be removing 15 pairs of vertices to see whether the graph is connected. No pair will disconnect the graph. Should we vote on it? Or should we just believe it? Okay, so that's one of the things that I want you to look at is the discussion. So I want you to look at the four questions in the 6.2.1. None of them are exactly this. So I want you to think about it. And notice IV. Can you find a cut S of G with order equal to 2? Can you find a cut with order 1 in this graph? No. That's pretty simple. You just remove one vertex at a time and make sure that what remains is connected. Okay, so the question IV is the best possible. If it's possible, it's the best possible. Okay, now for let's go to 6.2.2. Same question. What's the fewest number of edges to remove to disconnect this graph? What's the fewest number of vertices to remove to disconnect this graph? And let me remind you, these are pretty small graphs. I mean, I think even the Peterson graph has more edges, more vertices than this. You know, there are microphones on tables. You can talk to each other. Some tables, not all the tables.
Clearly 4 edges will do it. Can you find 3 edges? I have.
CD and U, what I see. WB. Which are the vertex C, D, and U.
Yeah, that's what we did.
You have this?
So it's actually 3, which is less than average. Which is exactly where's this graph?
With the same degree? On this problem or any problem?
Well, I was just looking at I.
Well, you're cheating. That's for homework.
Oh,
That's for homework. We're looking at 6.2.2.
What, 2? Oh, yeah, that's right. I'm sorry.
You can ask me that later. What are you thinking? What do you think?
We're talking about 6.2.2.
Move to the next page. 6.2.2. Sorry. The graph. Sorry, it's called figure 6.2.2. I'm sorry. I'm sorry.
It's on the same page.
Figure 6.2.2.
Oh, I see, they were doing that.
Is that
But it's
better?
not even really a problem, it's just. That's funny.
Were you right? No. Removing all the vertices of same degree of the smallest same
Well, I've been
degree.
thinking
All
about
of
it before
them?
that.
Okay.
Is
That would be
like
two.
what's like the minimum?
I think.
Which like this one.
I just thought it was cool, you like had that right off.
Well, I just realized that like I could have made a much simpler one that was just the same point. But
Yeah,
whatever.
absolutely.
Okay, you think about it. Stop.
因为比如说你想，就有一个这种，这边都是这样的，然后结果这有个点。
So we have,
You have a guess?
we do,
Uh-huh.
we have said that kappa G
W?
is 3 and kappa prime,
We
is
are-
that how you do
Yeah.
it? G is 4.
What is
Okay,
that?
so
So like
the 3, how'd you get the 3? So C, C, D. C, D. That I see.
So is it like,
That's
It's a
good.
cycle,
And then for 4, you just removed all the edges from
they're all
Any
connected
one.
to one vertex in the middle.
so it's like
On the edge.
Oh,
Yeah.
okay, all right, so that's a good question.
I can
I don't know if,
understand what
you
you
know,
said.
W5 means there's 5 rows on each side.
Okay, so I'm jumping ahead.
also, I was thinking, you know how, okay, so when we were doing like PN versus PN, right? So this is
The complete graph on N
This is
vertices.
N
This is the
vertices,
complete
right?
graph on N
Oh my
vertices.
gosh, I'm thinking, I forgot about the component
But
head.
didn't,
Well, this is all just one component, right? This, it's connected.
You get to
When you remove the edge.
The length of the
I was
pole.
thinking,
And it's nothing, it's far away from the degree.
I was thinking disconnection instead of component.
Uh-huh, right.
It's weird.
Okay.
So the length of this pad is N plus,
N minus 1, right? But it's,
The number of
but
vertices.
PN has N vertices, okay.
yeah, it's weird, sorry.
No, that's fine, I was mixing that up.
Because it's, you know, when you talk about length, I think the number of steps and that's the number of vertices.
Right.
But the size of the path, I guess.
Prime is the edges or the?
So K prime is the edge connectivity, and K is the vertex connectivity. So the order of the smallest set of vertices, smallest set of edges.
No, just make it.
I should order something like this without being,
Yeah.
I mean, I was like, I need to.
I actually thought of another way to prove
So
it.
that's a vertex cut and an edge cut. Okay, so one more time. There's a vertex cut,
What a minimum count is.
which means it's a set of vertices that disconnects the graph. That corresponds to the vertex connectivity. And there's an edge
Like
cut.
connection, but super contradictory.
An edge cut is the fewest number of edges, a set of edges, which disconnects the graph when you remove those. So there's the idea of a vertex cut and an edge cut. I want it all. I want it all. Oh, it just says cut, then that would be a vertex cut. Okay, 6.2.2. Consider the graph. Find a cut. Yes, a cut. Notice a cut is defined for vertices. An edge cut is defined. Okay.
So generally speaking, when we're talking about cut sets
So if you're looking
of
at.
vertices, you have two components, and
Okay,
this
so
would be
C
K-
cut out.
what we found.
Yeah,
So,
that's
you know, you're kind of
that's
looking
right.
at
So vertex, that's right. Kappa,
You're doing
kappa.
cut vertices, but you're looking for this structure when you're doing cut edges.
Oh, okay.
It's not quite vertex, because there's edges
Right.
inside of here.
Right. But you're looking for,
Actually,
yeah, for that structure where edges, a set, not necessarily all edges, but just a subset of the edges.
Right.
Connect to
connect to
partitions, partites of,
and actually,
connect to.
um,
Still have you They're not.
There shouldn't be any, well, there had better be edges on both sides, otherwise you can take,
Oh, there's probably a smaller set of edges.
right, exactly. You could take the vertex that's not connected to any of its friends and put them over here. It's cute.
So A, C.
The vertex cut is less than or equal to 3.
Thinking about
The
edge cuts of vertex.
vertex
cuts.
connect,
So,
this
you know,
one
can
here
you-
is less than or equal to
Maybe
3. So there's a
way
set
to
of
think
3
about it is
vertices.
like
This was
shuffling
6.2.1,
around the
so,
vertices from one side to the other.
the
Until you
vertices
get
you
down to
showed me
3,
were
it's possible.
W, B, and U. W, B, and U. Those 3 vertices, when I remove it, the graph is
It'd be
disconnected.
cool if these were like.
Okay, so it's less than or equal to 3.
I know 3 it works, but
Balls
if
and ropes or something
smaller than
connected
3,
to the
like
graph,
2,
you could just like
it's
move
done
all over
Yeah.
the place.
Yeah.
Okay, so now you have proof.
I wonder if we could.
Oh.
I mean,
Just
so,
edges.
I mean, you know, you could look at cases, but that's the hard part, is showing that I have one more time. So for 6.2.1, 6.2.1, you told me that WBU was a vertex cut. And so, in other words, when I remove WB and U, we have a disconnected graph. Turns out very disconnected, in fact, 3 different components. Okay? Theoretically, we're not done, because we have to show that that's the smallest number. Notice it's the order of the smallest set whose removal disconnects the graph. So what you would have to do, and of course there's only 6 vertices, I'm saying only 6, and if you want to look at every set of 2 vertices, by the way, every set of 1 vertex is pretty simple.
Right.
You can look at remove 1 vertex at a time, the graph remains connected.
No on 4.
But you now look at every pair of vertices, you remove those from the graph. If the graph is still connected, then we know that the vertex connectivity is greater than 2. Okay? The same goes for edges. If I remove any set of 2 edges, and there's a lot of sets of 2 edges, if I remove any set of 2 of these edges and the graph remains connected, then we know that it's greater than 2. So this would actually, that's why I have less than or equal to, because it's showing that it's equal, which when it gets hard. Okay. And actually blue is a question. So you're going to be thinking about, is the answer for 6.2.1 and is the answer for 6.2.2, whatever you give me, is it equal to 3 and 3, I believe. Okay. So what have you found out about 6.2, the figure 6.2.2? You're not saying much.
Well, we found that kappa G was 3.
You found, you believe it's 3. So theoretically, you've checked every pair of vertices, every pair of vertices.
Theoretically.
Theoretically. Okay. So, and what about 6.2.2 or 6.2.1?
6.2.2.
2.2. And what are your 3 vertices?
C, D, U.
C, D, and U. C, D, and U seems to disconnect the graph. What do I have left? I have the edge A, E, and the path B, W, V. So that looks to be a disconnecting set. Okay, what about a set of, that was a set of vertices. What about a set of edges that disconnects us? By the way, but 3 is less than the minimum degree here. One of the interesting things here is that it's not always the case that the connectivity or edge connectivity corresponds to the minimum degree. So this inequality remains an inequality. Could be strictly less. Okay, what about edges? For 6.2.2? You have four edges. Anybody? It's like an auction. I got 4 over here. Maybe we have 3.
You can actually fix any
You got 4? Sorry, you missed out. They bid you. Outbid you. Anybody for 3? Okay. So what I want you to do is think about. So this is what you need to think about is how am I going to prove? Look, this graph only has 8 vertices. I'm going to say it again. Only has 8 vertices. So I want you to think about how are you going to prove that the edge connectivity is exactly 4. By the way, what have 4 edges? Oh, there's lots of sets of 4.
Yeah, pick any
Any
vertex with a
vertex and
degree
take
of
all
4.
the edges. So it's that theorem up there. But is there a set of 3 edges that disconnects this graph? So, okay, and so there's more problems on the next page. And one that doesn't come up that he hasn't mentioned, I'm going to mention it. You know, this connectivity thing, that it can become fairly large. So we haven't looked at this graph in a while. What's this graph? It's a complete bipartite. K, in this case, K55. So what would be the edge connectivity?
5, 6.
5, 6. What would be the connectivity, edge and vertex connectivity of this graph? Questions? What do we got?
Would you think the vertices?
You think they're both the minimum degree? We know that it's at least the minimum degree, or at most the minimum degree. So if I remove all the edges from one of the vertices of degree 5, the graph is disconnected. If I remove all the vertices in the top piece, the graph is disconnected. So 5 looks like a good candidate. So in general, KMN, what KMN? Guess. I mean, let's guess.
I think in general with KMN it would be whatever the minimum degree is.
The smallest degree or the smallest part.
MNN, yeah.
The smallest part. Good. Okay. So that sounds good. So let me add to this. So you need more stuff to play with. Okay, so what do you think this means? K5, 6, 7.
Tripartite.
Okay, so it's got 3 parts. 1, 2, and 3. How big is the third one? Probably I shouldn't have made it so big. 1, 2, 3, 4, 5, 6, 7. And it's complete, so no edges here, and every edge. So you can figure out what the minimum degree is. And now the question is, what is the vertex and edge connectivity of, let's start with K5, 6, 7, but in general, KMN. Sorry, KMN, LMN. You gotta go in alphabetical order. So I take a set of L vertices, I take a set of N vertices, and I take a set of M vertices, put all the L's adjacent to the M's and N's, all the M's adjacent to the L's and N's, all the N's adjacent to the L's and M's. a lot of edges. What's the connectivity? Okay, that's for you to think about. And the last question, so is there a relationship between, in general, is there a relationship between the edge connectivity and the vertex connectivity? So if you, I want you to actually read through and do problems from up through 242 before 6.3. But I'd like you to read 6.3. 6.3 is the triple kappa, kappa prime, delta. Kappa is the vertex connectivity, kappa prime is the edge connectivity, and delta is the minimum degree. So that's the title of section 6.3. And we'll see that there's a relationship between those three parameters. Okay? There's lots of problems for you to work on. See you Thursday.
Okay. So this is what we were trying to prove.
Oh, yeah.
If Hamiltonian, then there's a